Hi everyone. I'm Aggraj Gupta. I'm a final year PhD student working with under the supervision of Professor Uday Khan Khoje. I'll be walking you through the topic RF design at lightning speed, structures in seconds. As you can see, the flash is here. So we'll talk how to design the structures in a blink of an eye. Okay, so several day-to-day devices that affects us. What normal people see. We do have mobile handsets, we do have Wi-Fi routers in our hostels, and we obviously use our cell phones that needs radio towers. But now what EE students see? We see this. So all the devices that you can see in the left comprises of complex circuits comprising of antennas, filters, power dividers, and many other circuits that I have not shown in this slide. So let's focus on just the antenna. What is an antenna in real? So this is how a microstrip patch antenna looks like. You have a patch on the top, you feed it by a source, some power goes in, some power comes out because of the impedance mismatch that you all will be knowing. So how do we say that your antenna is working? So for an antenna to radiate at a frequency f0, it should have minimum reflection. Whatever power you are sending in, the minimum power should go out. Most of the power should be fed to the antenna. And it should have maximum gain at the required frequency f0. So we sort of characterize a metric known as S11, which is a ratio of P out to P in, and we desire it to be below minus 10 dB, which essentially means whatever power you are sending in, 99% of the power is going inside the patch and less than 1% power is sort of coming back. So this is how a typical S11 curves look like. You can see at the frequency f0, there is a dip below minus 10. So what we say is that our antenna is working at f0. So P out is almost sort of 0 at f0. So we say that antenna is resonant at f0. And this is not the only important metric. We should also have a good gain. I mean, you are in a chamber where you don't have, suppose in our EE lifts, which is an anechoic chamber, we don't have any sort of signal reception, etc. So you need to have some gain so that it can work even when the signal is feeble, right? So gain is also an important parameter along with this S11 that I am talking about. So problem lies here. So do we want our cell phones to make calls but has no internet? Every other function that we have in our cell phones operates on a different frequency band. So do we want our cell phone to make calls but has no internet? Of course, no in 2024, right? So what design achieves, say, both GSM and Wi-Fi bands so that you can make call as well as use your internet? So we don't know the design. This is the problem. So, and we all want our cell phones to be compact, to work across all frequencies, and it should, wearable stuff that is sort of going on these days. So we want compactness. So how do we sort of design compressible antennas? Let's take a motivation from the image space. Consider a very tiny binary image of a 20 by 20 pixel. Possible number of combinations are 2 to the power 400, which is greater than 10 to the power 80, total number of nucleons in the universe for just a tiny image. So in this megapixel, all of us, whenever we are going to buy a cell phone, we see how many megapixel camera do we have. In the entire megapixel space, the natural image space is very tiny. And we sort of try to find the other representations that can be sparse so that our images can be compressed. You send your images on WhatsApp. If an image file is 8 MB, it's going to take a huge lot of data. What WhatsApp does, it sort of compresses the image and it's just of orders of KBs. So this is how the natural image space is. It's compressible. So let's think of an antenna as a binary image. So this is how a typical microstrip patch antenna looks like. And you can see we can only control 2 design variables here. But what if I tessellate it to, say, exponential space? We expect it to get compressed as per the analogy I have given from the image perspective. So the conventional way of designing the structures that we usually design are structures. So most of the solvers that we sort of have in our hand, we design something, we see the response, again we tweak the design. This is an iterative process which is time consuming, and although being accurate, these solvers are very slow. So this is how a typical design looks like. You go on tweaking the structure, whatever frequency you need in, and you have to change the design aspect every now and then, which is expensive. So, and the things get even worse when you have, this is just for a single band. As I was saying, if you want multiple bands, you don't know the physics of this device. So how you are going to design the device? So the problem becomes even severe when you go ahead with your multi-bands. So resonance complexity is there. So how to unlock this frequency band? We need lots and lots of domain knowledge and multiple time expensive solutions. So how about if we replace this time consuming block, that is our solvers, with the AI based model? So this is how a typical AI model training looks like for the people who are not very familiar with the AI background. So we have input X, we have some output Y. So typical data set consists of X and Y pairs, and we sort of learn the network parameters. That is how we train the model. So backpropagation essentially is you just need to find the gradient of the function so that we get some good relation between X and Y that we don't know analytically. So the goal of the network is to learn a complex relationship between the variables by minimizing the loss function, since you don't know any analytical thing about the function. So I have sort of infused AI in the design machinery, which is the forward model that I'm calling. So I have replaced the full wave EM solver by a cheap to evaluate AI model. The bottom figure is the typical convolutional neural network. It sees antenna as an image, it predicts the spectrum. And this is very fast. So if you see, the design time for the conventional EM solver is 3 minutes per iteration, and based on your knowledge and experience, it can have n number of iterations. So it can take from hours to days, but the AI model can predict in less than 1 second. So how good is our surrogate model? And we can see from this slide that the forward model predictions and the full wave simulations are sort of in agreement with each other. And this solution sort of mimics a conventional solver that predicts the response in an ultra-fast sense. And the package used to sort of come up with this model, we used MATLAB and Python. So using the developed, so the goal was to generate an antenna given the response. So what we have currently is this. We have our antenna. We sort of pass it through the forward model. It predicts the spectrum. Are we done? Did we get our antenna in hand for a given spectrum? The answer is no. So we will be using this cheap to evaluate solver that we have just developed to design a device. That is why we are calling it inverse design. Now we have the spectrum, but we need the device. So where do we need to go? We need to go from spectrum to device. We should have gone directly also, but then why do we need this? Why to invert the network? Answer is in this graph. Data inconsistency that we say. For two different designs, DA and DB, we are having almost the same spectrum, which means the training is never going to converge. So that's why we have to invert the neural network. This is the basic motivation why we are sort of wanting to invert the neural network. So this is the developed AI-based EM emulator that we have developed for the design device. You can see, and at the input, it is the spectrum that we sort of want. In the there are a few layers, fully connected layers, and there we have developed the activation function, which is novel because usually in AI architecture we don't do binary optimization because of backpropagation. We need to take gradients, and the activation function should be differentiable. Otherwise, you won't be able to learn the network parameters. So we have developed this ST activation function, and if you train this network well, you can sort of extract your design in less than a second. So this is the equation of the ST activation layer that we came up with. So it sort of takes a real value, but it clips, it sort of thresholds the value to some binary values, ones and zero, being differentiable. So this layer is integrated in our AI model. But challenges and trade-offs. Let's see the challenges involved in using AI. So deep learning networks have no idea how your antenna or how your any typical structure looks like. So you have to use a suitable loss function to train the network, guiding it towards meaningful device, because it doesn't know how the device, it doesn't know about the device physics. We have to train it intelligently. So input is the design, output is the spectrum, loss function is spectrum loss. What is spectrum loss essentially? We sort of, try to align the prediction to the desired spectrum. As you can see, during the training, it sort of tries to approximate what the ground truth is. Based on this, it learns the network parameters. But the antenna that we get is this. You can see the brown pixels are copper, the white ones are dielectric. So you can see this is a very sort of bad looking antenna because the copper metals are not connected. It's not gonna radiate. That is what the deep learning network gave us. What if we use spectrum loss plus binary loss? But what is binary loss? We just sort of penalize the loss function to say that, if the resulting structure is not binary, increase the loss value and then learn the network. So basically, for the binary structure, it will be just the spectrum loss. For the non-binary structure, it has to offer a more penalty, ls plus some non-zero number. And we see the structure that we get is this. Why? Because, it stucks into the local minima, and you can see very few pixels are completely brown or white. There are somewhat, in between pixels that are not binary. Our antenna was in the binary space. So then we sort of trade with the design loss. What is the design loss? It sort of penalizes the structure that are far away from those in the data set to get the more meaningful designs. Then we sort of did, and again we were not getting good structures. What if we put all the terms in the cost function and see if at all we are able to get our antenna? So by bundling all the loss functions, by bundling all the losses into a streamlined function, we nailed the antenna design for the peak performance. And this is now how my antenna looks like. We have got an antenna with this loss function and the ST activation layer that we have proposed to optimize AI model binary for the binary optimization. One more trade-off that I want to talk about is deep learning networks are just the interpolators. So if you have samples at some frequencies, say f2 and fn minus 1, and your design frequency is in between, you'll be able to design a structure. But if you don't have your samples at f1 and say fn, you won't be able to design a structure. These are just the interpolators. But for RF people, photonics people, we work in a certain frequency span, so frequencies are important. And what we have observed was, this is the top right plot shows the number of spectra in the data set. We see we are able to design the devices where there is the peak of the resonance. The reason is because the data set is imbalanced. My data set is too much biased for some frequencies, but it's not able to inverse design it for some other frequencies. This is what the limitations of AI is. How do the inverse design structures look? This is how they look for a single band and a dual band antenna. We have got a recent paper in transactions on antenna and propagation last year. And so now everything is okay. We are sort of doing simulations and everything looks fine. But to complete the loop, let's see, do the inverse design structures work in real? And yeah, it does. So we have also fabricated the structures, single band and dual band. And surprisingly, the structures are 50% compact. And we can see the performances are good. So overall, to sort of coming across all this problem of inverse design, it takes the entire loop of study. So first you have to understand the device physics, formulate the problem, generate the data set, develop the AI model, verify the structure, and finally fabricate and test it. So it's a complete loop now, and we are able to test our devices as well as and the methodology that I have sort of shown here is very general. I have shown it for an antenna, but it can definitely be applied to other devices as well, as far as you can parameterize your device well. So for all these skill sets and that I have developed during my PhD tenure, I sort of thanks my advisor, Professor Uday Khan Khoje, and this is our group photo. We sort of work in several areas of wireless power transfer, intelligent reflecting surface, OAM, and writing solvers for various applications. And our work sort of intersects between physics, maths, and machine learning. So we broadly work on inverse problems. And yeah, thank you.